Hello everyone, today we'll talk about 3D SIS, 3D Semantic Instance Segmentation of RGB-D scans. So this paper is mainly trying to solve a task of semantic instance segmentation, which is well known in computer vision field. The task is mainly aimed to get the bounding box, class, and per voxel masks for each object in the scene, and the novel point for this paper is they try to fuse both color and depth features. Why do we want to use RGB-D as our input? Firstly, those kind of sensor is very available with low price and mature code base, and we already have a lot of development in the 2D computer vision part, and if we can use the color signatures, maybe we can adopt those invented wells to 3D parts. Yet we are, after all, treating a 3D task, so depth map should be the focus. The contribution for this paper is they propose a network to do the 3D semantic instance segmentation and got the new state of art. To do that, they fuse both color and depth features, and they use a novel back projection method, as well as extending the 2D mass SIS pipeline to 3D to achieve that. The problem setting here, the input is a RGB-D scan, the depth will be a truncated SDF, and then there can be multiple images associated with it, and each one will have its own camera pose. The output is the bounding box, the class prediction, as well as a per voxel 3D mask. As we said before, the method is extended from mass SIS, so it's easier to understand 3D SIS if we know the pipeline for mass SIS, which consists of 5 parts. First one is a backbone to extract the image features. Second one is a region proposal net, which will propose a set of anchor points that may contain objects, and each anchor's features will be extracted and passed through the region of interest network that can unify the size for each anchor, and then the unified features will pass into detection and segmentation heads. Here is the 3D SIS architecture. As you can see, it still have the same 5 components, yet each is adapted, is changed to adapt the 3D use case. For 2D backbone, the major problem to solve is how do we project the 2D color to 3D geometry. The naive way will be a direct projection, yet the image resolution is much higher than the voxel resolution. Then this will cause a very huge downsampling issue. A better way will be, this paper proposed, is use a 2D backbone. Here is a pre-trained ENAT to extract the color features and reduce the resolution before doing the projections. To handle the multi-view, they max pulling on the 3D features instead of the 2D features, as the 2D features is not the same 2D location doesn't actually map to the same 3D location in different pictures. And to fuse with 3D, they got we have the 3D color feature. It will later on be concatenated with the 3D geometry features. For the 3D geometry backbone, here is the voxel dimension. Set it in the training and testing case. And for the 3D convolution, they use a 3D ResNet, and then the color and 3D is passed through the ResNet first before joined together for later on tasks. And one interesting part here is they use a 2-branch backbone. The detection branch reduced the spatial dimension size by 4, yet the segmentation branch maintained the same dimension. This can improve the result and the training time. Second part is the 3D region proposal net. What it does is it will put a series of anchors and then decide whether each anchor is useful or not. The anchor size is determined by running a k-mean on the training data and split the anchor size to two groups, the small and large. Each one will have its own ROI and RPN network, supposedly to increase the model's ability to handle both small and large atoms. And for each anchor point, it will first be classified whether it's positive or negative using our objectness score, and then it will also predict a shift and scaling variables from the anchor to the actual bounding box. Once we have the bounding box, we can crop out the features and then select the corresponding one with high objectness, and we can pass it to the ROI. ROI is mainly used to unify the size of for each anchor, and the major method is either ROI pooling or ROI aligned. ROI pooling is the top one, which use a pixel coordinate that can lead to more quantization error. ROI line use a floating point grid system, which is more accurate. Here they use ROI pooling to get the unified feature, and then later on to get the class prediction. For the segmentation, what it does is they crop out the feature using the bounding box, and then use the features to pass into the mask prediction head to get the per voxel mask. The major takeaway here is the voxel resolution is very important. The paper stated that if we do a reduction of the resolution similar to the detection branch, it will impact the performance heavily. This may due to the original low resolution nature of the voxel grid due to the limitation of computational power and memory. Here is the training set. First one is ScanNet, which is real world data. Second one is SunCG, is simulated. Both of them consist of the depth image and the RGB image, as well as the camera pose. Here is the result. As you can see in the ScanNet, 3D-SIS beats both depth method or RGB method and got the state of art. And in SunCG, it beat the other method as well. Also shows the effectiveness of multi-view and the color information. Here is some results. So major takeaway here is 3D-SIS got overall improved result, and it also shows the effectiveness of the color and geometry fusion both in SunCG and ScanNet, as well as a multi-view boost. As we can see, when we add more views, we got the better MAP on both the synthetic and the real data set. So what's the critic and limitation for this paper? Firstly, they only use ROI pooling but not using ROI aligned, yet in 2D computer vision tasks, it's already well known that ROI line can increase the performance compared to ROI pooling. It would be good to at least try ROI line and see if it also works in 3D. Secondly, although the whole network architecture is heavily influenced by the limitation of voxel resolution, the author doesn't really go into the depths to understand why this part is very important, although we know that the low resolution of voxel can have an issue. Third one is they talk about the marginal effect of multi-view and show the comparison between no view, 1 view, 3 view, and 5 view. Yet within a SunCG, you can actually easily get more views from each scene. Maybe we can create much more views and see what's the marginal return for the adding multiple views, and either like a sampling from different trajectory or like a different sampling method can improve this. Yeah, and I monitored Piazza discussion. There is not much questions about this paper, so that's it for my presentation.